Hi, this is Nat, and this is going to be a challenge video lesson on using alternative base systems. You might remember in a previous lesson on place value hearing that our base 10 system is not the only possible way of representing numbers, and we're going to actually kind of dive a little bit more into that idea in this lesson. If you recall, our place value system is based around groups of tens. We call it a base 10 system. But there's an infinite number of possible alternative ways of arranging numbers. That said, every single system works in kind of the same way, so we can use what we know about our base 10 system to help us understand alternative base systems. So that's the goal for today. We want you to be able to use what you know about place value and apply it to different base systems. Let's start by doing some examples. Here we go. If we look at these red blocks here, and I asked you to count these, you probably would count those and say, okay, there are 17 blocks. And that's because you would intuitively be counting in a base 10 system, in which you would have started counting and said, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You would have grouped your first 10 into a collection, and then you'd say, okay, so there's one set of 10 and 7 ones. So in a base 10 system, which is what we naturally intuitively use, this set of red blocks is represented by 17. Let's change things up a little bit though and say that we actually didn't use a base 10 system. Instead, we use a base 5 system. There's no reason at all that I picked a base 5 system. It's just the first number that came to my head. But in a base 5 system, we'd be, again, grouping, but we'd be grouping not in groups of 10, but groups of 5. Every time we got to 5, we would regroup. So if I'm counting this in a base 5 system, I'm going to say there's one group of 5, one group of 5, one group of 5, and 2 ones left over. So in a base 5 system, I'm actually going to call this number 3 groups of 5 and 2 ones left over. So in a base 5 system, this is not the number 17, this is the number 32. And again, there's an infinite number of ways we could do this. So let's look now at a base 7 system. In a base 7 system, I'm going to regroup or group in sets of 7. So if I look up here, here's a group of 7 right there. Here's another group of 7 right there. And there's 3 ones left over. So in a base 7 system, there are 2 groups of 7 and 3 ones. So in a base 7 system, this number would be 23. We could keep doing this forever, but we're going to actually just do it maybe one, maybe 2 more times, we'll see. But let's actually drop down into a really low base value system. We're going to go base 3 this time. Because in a base 3 system, some things that you've been doing that might have started to seem like, oh, that makes sense, are going to start to look even weirder. So in a base 3 system, you might guess we're going to be doing groupings according to threes. So I'm going to be looking for sets of threes here. Here's a set of 3, 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 here's a set of 3. The natural tendency is going to be to call this 52, 5 sets of 3 and 2 ones, but that's actually not correct. Because remember, in a base 3 system, we group in threes, and whenever we get to a group of 3, we regroup again. So in this case, 3 groups of 3 is actually a new grouping. Let me put that in a different color to make it easy to see. We have 3 groups of 3 up here. So when I write this number, I'm going to call it one group of 3 groups of 3, one group of 9, we might say, 2 groups of 3, and 2 ones left over. So I actually got up to what I think of as the hundredths place, or hundreds place, but in a base 3 system, this is actually the nines place, that third digit over. We could take this idea one step farther and actually go into a base 2 system. This is also known as binary. It's the number system that computers use for a reason we're not going to get into right now. But we can do the same thing again. So we're starting off looking, because it's a base 2 system, for groups of 2. So here's a group of 2, here's a group of 2, group of 2, and so on. I've got a whole bunch of groups of 2. I'm going to kind of pair these up as best I can. Okay. Every time I have 2 groups of 2, though, now I have to regroup again. So let's take these 2, and that's going to be a big group of 2 groups of 2. There's another one. Let's see. Here's another one right here together. Here's another one. So I actually have regrouped all of my groups of 2 into bigger groups of 4, 2 groups of 2. Now I have to do that again. Any group of 4, or any 2 groups of 4, I have to regroup again into a group of 8. So here's a big group of 8, and here's a big group of 8. So I've regrouped again. And I've actually got 2 groups of those, so they're going to have to be regrouped one more time. And I'm running out of colors here. But basically, all of these get regrouped into a single big group. And when I write this, what I'm going to say is I've got, to start with, a single group of 1. That's my ones place. I don't have any groups of 2 left because I've had to regroup them all. I don't have any groups of 4 left because I've had to regroup them all. I don't have any groups of 8 left because I had to regroup them all. But I have one group of 16 that they eventually all got grouped into. So actually in a base 2 system, this number is going to be 10,001 because of all that regrouping that I had to do. Now that might seem complicated, but it's an interesting thing to kind of think that a base 10 system, like the one that we use, would seem complicated to anybody who is not used to that. So all of these things functionally work the same. It's all based around kind of what you get used to working with and what you end up being comfortable with. So we're comfortable with a base 10 system because that's what we see. Other people would be comfortable with a base 3 or 7 or whatever system if, they lived on some other planet. The other thing that's interesting to think about is that we never changed the number of red blocks that we had here in the picture. So each of these numbers that we've written over here on the right represents the exact same amount of stuff. But depending on the base system you're using, it's represented in a very different way. So 17 in base 10 is the same as 32 in base 5, is the same as 23 in base 7, and so on. The other side of this is thinking about what's the value of a number in different systems. So if we saw anything from the last set of examples, it's that the numbers we use could mean different things depending on how you group. So we're going to take, for example, this 23. How much is 23 in a couple different base systems? Let's start off with, say, base 5. In base 5, we regroup in sets of 5. So the ones place is always the ones place. So when I look at this 3, no matter what system I'm using, it's always just going to be 3 ones. So that's easy. When I think about the 2, that's what might be different. When we look at the 2, that is, depending on the base system, a very different set of numbers. 2 sets of 5 is very different than the 2 sets of 10 that I'm used to looking at. So if I'm looking at 23 in base 5, well, I've got 3 ones, and I've got 2 groups of 5. And the grand total there is 13. So in base 5, the number 23 is not really 23, it represents what I think of as 13. What about in base 8? So in a base 8, things are still the same. 3 ones is always just 3 ones, but 2, in this case, is 2 groups of 8. Well, if you're good at multiplication, you probably think to yourself, well, that's easy. 2 groups of 8 is 16, and that's totally correct. So 16 for that 2 groups of 8 plus your 3 ones means that in base 8, this number is actually representing the number 19. All right, let's do 2 more. let's go base, what haven't we done? Base 9. So in base 9, 3 ones is still 3 ones, but 2 sets of 9 this time is going to be 18. So 18 and 3 ones gives us a grand total of 21. So this number in base 9 would represent what I think of as 21. You're going to notice as the base system gets higher, closer to the base 10 that I'm used to, it gets closer to the 23 that I kind of would expect. Very last one. Let's think about a base 3 this time. And we're not going to go too far into this because it's really a trick question. That's intentional. I want to think about why this was a trick question. It can't be a base 3 system. There's no such thing as this number in a base 3 system. And that's because you can never have a 3-digit in a base 3 system, because if you got to 3, you should have regrouped up. So that 3 in the ones place here would have gotten actually regrouped. It couldn't stay at 23. It would have regrouped up to a 3 in the tens place, what I think of the tens place. And that actually would have regrouped again up to a 1 in the hundreds place. So 100 would be more of a base 3 value. But the point here is that it doesn't exist. This is not a base 3 number. Just like there's no tens digit in a base 10 system, you never see a 3-digit in a base 3 system or anything higher. It just doesn't work. So you're going to get a chance to play around with these ideas, converting numbers from our base system to other base systems. Like we said, there's a whole lot of different ways you can organize numbers, and if you can understand the way that numbers are organized in other systems, it'll help you better understand the way that we organize our numbers. There's nothing exceptionally good or perfect about a base 10 system. That's not why we use it. It just happens to be the number system we use, probably because we have 10 fingers. All the different number systems that we've seen here have their relative, strengths and weaknesses. We could use them in other scenarios just as successfully. So it's worth understanding, and hopefully it'll help you get better with our base 10 system. And that's it for this lesson. Take it easy.